Meet SAE International. You might not know us, but we've been with you. For the past 100 years, we've been revolutionizing transportation and mobility, partnering and supporting the dreamers, innovators, and can-doers who are changing the world. It's the child whose future career as an engineer will be shaped by our STEM education programs. It's the businesswoman boarding her flight with peace of mind, knowing that our committees have created the standards that ensure she gets from Detroit to Delhi and back again safely. It's the parents-to-be who are sleeping soundly, knowing that their electric car is fully charged and ready when it's go time. Driven by a passion to advance mobility knowledge and solutions, SAE's global community of over 200,000 engineers, technical experts, and volunteers continues to develop and curate the most reliable and comprehensive collection of engineering resources and consensus-based standards on Earth. The next mobility revolution is upon us. Connected and automated, electrified and sustainable. SAE will be here, as we have for the last 100 years, moving the world forward.
Welcome, everyone. My name is Chris Rovik, and I'm the Executive Program Manager of Electrified Heavy-Duty Truck Programs in the Advanced Product Planning Office at Toyota Motor North America. Thank you for joining us today, and to SAE Detroit section for hosting this event. Today, we're going to be talking to Scott Friedman, who's Senior Engineer of Advanced Product Planning Office in Toyota Motor North America's R&D. And we'll be talking to him about our Toyota's hydrogen fuel cell development for heavy-duty truck applications. So, Scott, welcome.
Thank you, Chris. Hello, everyone. Thank you for taking the time to join us today. I will go ahead and share my screen with our presentation. So let's get started. So today's presentation, we will first cover who we are as Team Toyota. We will then take a look at the evolution of Project Portal and the powertrain of our team that our team has been working on. This will lead us into a brief tour of our facilities and a ride and drive with our very own lead driver, Danny Gamboa. Finishing up, we will take a quick look forward, followed by some Q&A. As Chris had mentioned earlier, please don't hesitate to put your questions into the chat. So Toyota Motor North America, our footprint expands across a network of 1,500 dealers, 14 manufacturing plants, 16 research and development facilities, and the list goes on. Our headquarters are in Plano, Texas. However, our main R&D facilities are located in the greater Ann Arbor, Michigan area, and other offices in Gardena, California, and Whitman, Arizona. So at Toyota, we have a company culture derived from our founding father, Sakeiichi Toyoda's guiding principles. Always be faithful to your duties, thereby contributing to the company and the overall good. Always be practical and avoid frivolousness. Always have respect for spiritual matters and remember to be grateful at all times. Always be studious and creative, striving to stay ahead of the times. And lastly, always strive to build a home-like atmosphere and at work that is warm and friendly. So Sakeiichi's great-grandson, Akio Toyoda, has continued his great-grandfather's legacy from leading the transformation of Toyota from an automobile company to a mobility company, paving the way for projects such as ours. So what is Project Portal?
This is a story about a very innovative truck. A truck that cleans the air as it drives. And this story begins in a world where every day a steady stream of pollution is released into the air by over 2 million trucks as they transport goods across the country. So what if all those trucks did the same amount of work, but didn't pollute at all? This is Project Portal, a collaboration between Toyota and Kenworth to produce an emissions-free, heavy-duty semi-truck. Instead of a diesel engine, this Class 8 truck is powered by a hydrogen fuel cell electric system. As air flows through the front grille, oxygen is channeled to the fuel cell behind the cab. In this fuel cell, the oxygen is combined with hydrogen to create electricity. A lot of electricity. Enough electricity to drive a 560 horsepower electric motor that can propel the heavy-duty truck for up to 300 miles. All while emitting no smog, no soot, only pure water. In this world of big trucks, innovative technology can make them cleaner, quieter, and more productive than ever before. This is just the start of Toyota's vision for a world where innovative technology helps reduce our impact on the environment. This is Project Portal.
So how did all this begin? In 2014, and after 22 years of development, the Toyota Mirai came to market. This was the first mass-produced and commercially sold fuel cell vehicle in history. Shortly after the release of the Mirai, in 2015, Toyota announced our Environmental Challenge 2050. Based on our deep respect for the environment and in the spirit of challenge, Toyota took a good look at our global environmental impact and footprint, not just our company, but our entire supply chain. With that, 6 key challenges were identified. The first challenge was achieving zero. So reducing global carbon dioxide emissions, completely eliminating all CO2 emissions through the entire vehicle life cycle, and achieving zero CO2 emissions at the global plants. The second part of the challenge was net positive impact on the environment, minimizing water usage and implementing water discharge management, promoting global deployment of end-of-life vehicle treatment and recycling technologies, and connecting with nature conservation activities beyond the Toyota Group and business partners along with communities. So looking at the entire supply chain and coming need for zero-emission vehicles, we unveiled Alpha Fuel Cell Electric Class 8 proof of concept in 2017. We took fuel cells out of two Mirais and added 2 heavy-duty electric motors and new batteries to pull 80,000 pounds near the port area for local operation. Shortly after Alpha was unveiled, in November 2017, the San Pedro Bay Port's Clean Air Action Plan was updated. Knowing that the ports would like to expand by up to 50% by 2030, the ports at the same time couldn't just increase pollution by 50%. That is where the 2017 Clean Air Action Plan update comes into play. This was a public policy stating a goal for the future of the San Pedro ports. All import operations converted to zero emissions by 2030, and all trucks going in and out of the ports to be zero emission by 2035. Zero emission vehicles are required to meet these aggressive targets, but at the same time, there weren't too many solutions out there. But let's take a step back and see why this was so significant. The San Pedro Bay is home to ports of Los Angeles and Long Beach, the number 1 and 2 busiest ports in the United States, larger than the next 37 states combined. Millions of these containers moving in and out of each year require heavy-duty trucks to take them from shore to store. All those trucks moving from the port through disadvantaged communities presents a very real health risk. Asthma and other respiratory diseases, along with certain forms of cancer, are unfortunately commonplace in those communities. Imagine what all those communities could look like if trucks driving through were just emitting nothing but water and some good vibes. Well, thanks to the ongoing pandemic, we don't have to imagine it, we can see it. On March 2nd, 2020, the majority of California, like other states around the country, went into lockdown. One silver lining that stands out is that the nitrogen dioxide levels, as seen by NASA, clearly reduced over the time during the shutdown. It is possible to make an impact on the environment in a positive way. Project Portal is only just a small step in the right direction. So let's get back to the timeline. Leveraging the innovations of our alpha proof of concept and the renewed motivation from the Clean Air Action Plan update, the beta prototype, or Project Portal 2.0, was unveiled in Traverse City, Michigan at the CAR Management Briefing Seminar in 2018. Roughly a year later, in 2019, through CARB's zero and near zero emissions freight and facilities, or ZANZEF grant, Toyota and Kenworth debuted the first of 10 fuel cell electric trucks. Fast forward to November 2020, despite the pandemic, Toyota and Kenworth began delivering fuel cell electric trucks to our pilot partners after being extensively tested at both the PACCAR and Kenworth and Toyota proving grounds. To date, we have logged just over 40,000 miles of zero-emission Class 8 trucking, including with our partners, TLS, UPS, TTSI, and Southern Counties Express. Learning tremendously from our ZANZEF partners, in December 2020, Toyota commissioned the next prototype fuel cell electric truck. Using the next generation fuel cells from the all-new 2021 Mirai, we designed an integrated dual fuel cell modular system with emphasis on the truck OEM. This was a significant leap towards a production-intensive product. And in August of this year, we announced that our friends at Toyota Motor Manufacturing Kentucky will be assembling the integrated dual fuel cell modules beginning in 2023. Those same integrated dual fuel cell modules were on display this year at the Advanced Clean Transportation Expo in Long Beach, California. Here it is in our booth alongside a diesel for comparison. We designed the module to fit in the existing packaging space of a diesel in order to minimize the amount of redesign our truck OEM partners would need to, while accommodating a zero-emission powertrain. So how does it all work? The fuel cells are only one piece, but a significant one. We combine it with high voltage lithium ion battery, hydrogen storage tanks, and a dual motor and transmission. We've also leveraged our state-of-the-art hybrid synergy drive to control the logic of power split between fuel cell and battery power. We have two modular systems running in parallel to deliver the power Class 8 truck drivers need to haul freight. As stated in the previous slide, here's a general look at how our fuel cell Class 8 heavy-duty powertrain kits fit into an existing truck chassis. We have the integrated dual fuel cell module assembly located in the engine bay. We have a high voltage battery located under the cab. The hydrogen storage is behind the cab. And lastly, the electric motor and transmission assembly is located between the frame rails. So keeping in mind the needs of our truck OEM partners, we streamlined the interface to our kits. A single low voltage connection for CAN communication, a start signal and hardware enable, a self-contained and isolated 12-volt power supply, dual high voltage connections for the electric motors and truck side components, a single air intake interface, an integrated hydrogen supply, and lastly, a simplified CAN message interface for controls and communication. Let's now shift a little bit and take a tour of our integrated dual fuel cell assembly, our state-of-the-art evaluation bench, and a ride and drive around the Port of Los Angeles.
everyone. My name is Scott Friedman. I'm a senior engineer here at Toyota Research and Development. What we have today is our heavy-duty fuel cell assembly. It's a modular assembly, uses 2 fuel cells out of the current generation Toyota Mirai. What we've done at Toyota is been able to package our fuel cells into a modular setup with all the balance of plant inside. The balance of plant is located in different areas based on the shape of the module. What we've done is put the 2 modules together in a parallel platform, had a single point of interface with the truck side, either hydrogen supply or the cooling. Basically, what we've been able to accomplish is a complete drop-in for a diesel truck. As you can see, we have one interface for air intake up here. We have our ion exchangers. We have each of the fuel cell modules below. On the back side of the module over here, we have our high voltage connections, supplying 2 buses of high voltage power. As you can see down below, we have connections for our cooling system, our power electronics cooling. We have our low voltage connections and our relay boxes self-contained for each of the modules. With this setup, we're able to produce an enormous amount of power for Class 8 heavy-duty trucks. This is a first for Toyota, and we hope that we see this more proliferate in the years to come. In the future, we plan on providing these to truck makers, so we would like to provide these to our truck partners, produce these as zero-emission trucks for the Port of LA, Port of Long Beach, Southern California, and eventually Northern California as well. Toyota itself prides herself on the hydrogen technology that we've developed over the past couple decades. So we like to see this take it into the next step and be able to have a hydrogen society as well as a zero-emission future. We have test trucks in the field. Some are ranging in the 300 miles per fill-up range. That's for 60 kilograms of hydrogen. They're actually being tested in the Port of LA and Port of Long Beach, also out to Ontario, California now, gathering data. But it is very dependent on the type of routes that customers will choose, also the payloads and so on. Benefits for hydrogen, especially in the heavy-duty space, is refill time. So trucks aren't going to stay at a station for multiple hours. We also understand the footprint for a charging station versus a footprint for a fill station that we've already taken a look at. Being able to have one fill station for multiple trucks instead of multiple hookups for different battery electric vehicles. We also know that onboard storage is a big thing. The mass of a ginormous battery could take away from the potential total cost of ownership and return on investment for our heavy-duty partners.
Hi, my name is Janice Turon. I'm a technical manager with Toyota Motor Europe on assignment to Toyota Motor US. I'm here to explain what we have in our facilities in terms of fuel cell evaluation. So what we have here is a test unit that is used to evaluate the powertrains of heavy-duty trucks. This is a brand new facility. What you have here is the full assembly, the 2 stacks. This unit needs several things in order to run properly. There are cooling pipes, there are hydrogen lines, there are high voltage cables, and all of these things need to be supported by the facility that we have around us. On this side, we have the hydrogen supply, which as of now, it comes from those hydrogen bottles because we're in the commissioning phase. But in the future, it will come from the station in the back. There's going to be a pipe that will supply all of this hydrogen for extended testing. The other thing that we have is some coolant loops. So this provides the cooling to the power electronics as well as the fuel cell stacks. These are 2 separate cooling loops because they need different type of fluids and different cooling requirements. Another important component of this testing station is the exhaust of the fuel cells are connected through these pipes out to the outside. So here, because this is a fuel cell, we're generating water as a result. So we need to separate the gas and the water. This is done in those containers back there. The water is simply run through the normal sewer pipes, and then the gas exits out on top of the building. The high voltage cables that you see here are connected to the cabinet on this side. And what that does is it sinks all the energy that's being generated by the fuel cell stack. Eventually, we want to be able to evaluate the full powertrain. So that includes not only the fuel cell stack, but the battery and the motor and the transmission itself. So this is why we have all of these components. By using this junction box here, we can connect these different components together and we can connect the high voltage output from the battery and the fuel cell to the motor on that other side of the room. So let me show you a little bit in terms of the energy that's being synced into the power grid. We're doing this in this room over here. These are our battery emulators. So these 4 cabinets provide 250 kilowatts of power each as energy source or energy sink to the units that we're testing. Finally, I would like to show as well the dyno. So this is the dyno that we will use to connect the motor and transmission to. This will provide the possibility to sync the mechanical energy that's generated by the motor. This is obviously in the process of being set up. Once it's ready, we will have up to 1.2 megawatts of power that we can use for our testing.
Hi, my name is Danny Gamboa, and I'm the lead driver for Project Portal here at Toyota. Fueling a heavy-duty truck is really easy. It's very simple. We basically just connect this nozzle to the receptacle and hit the start button. Fueling usually takes less than fueling a diesel truck. It takes about 15-20 minutes. I've been driving for over 20 years. I've been in this industry, not just driving, but also in management and in safety. So I've seen both sides of the wheel, where driving trucks and then also managing the people that drive trucks. And then also in logistics and planning. It's a really big industry. The biggest difference in driving a fuel cell truck is like the amount of torque and power that's available to you. It's really quiet and smooth and very few vibrations, which, you know, leads to me not being as tired at the end of the day because there's not as much vibration, there's not as much noise. The best part of my job is, you know, driving and braking trucks and really testing trucks to their limit. The amount of power of these trucks, they're easy to drive and they're fun to drive. You can't do that on a diesel truck. You can't just accelerate like this with this much instant torque available. As you can see, it's a very quiet ride. It's very smooth. As we are delivering freight, as we are delivering a bunch of loads, we're not polluting in the community in which we're driving in. And that to me is the biggest plus. That's why I'm here. Making a better world for everybody and having clean air, which is, you know, that's everybody's goal, to reduce greenhouse gas emissions and have a better environment for all. Because I grew up in Long Beach, so I live near the port. I grew up near the port. Like, I have asthma because I grew up near the port. So this technology here will definitely address those issues. We estimate that the range of this truck is 350 miles on a full tank of hydrogen on these trucks. Light duty and heavy duty can both fuel at the same station if necessary. These are designed for drayage. They're designed for port. Currently there are 3 fueling stations, commercial fueling stations for heavy duty trucks that are online or in the process of becoming online. In addition to those 3 commercial stations, we have a station at our Gardena facility. You know, we get a lot of thumbs up from other truck drivers when we stop at stoplights. They're like, whoa, what kind of engine do you have in there? Because they see that we have a lot of power and torque. So the power in this fuel cell electric truck is equal to or greater than a traditional truck. In the future, this is the type of power that drivers are going to want to drive. We have more than enough power to deliver freight. It doesn't burden communities with pollution. So that to me is the reason why I'm here. If we can find a way to still deliver freight, but not burden communities, polluting them with exhaust, then that's a win-win.
All right, thanks, Danny. So looking forward, we have some challenges and opportunities ahead of us. So we've seen that we've been able to take the technology to great leaps from proof of concept into something that's more production intent, but there's still a way to go. So challenges of heavy duty ZEV adoption, we highlight two key areas. The first one is market adoption. Much like in light duty, we are studying infrastructure. That's always somebody's question. Total cost of ownership and return on investment, as well as fleet flexibility. On the other side, there are technology challenges themselves. Going from a traditional diesel to an electrified powertrain, regardless if it's fuel cell or battery, requires other truck side components to be electrified as well. Think a traditional cooling fan, once spun by an engine, now needs to be electrified. Same with a brake air compressor and also solutions for Jake braking. So let's talk infrastructure for a second. In the state of California, as of today, there's about 49 stations for light duty in operation. As Danny had mentioned, we have about 3 heavy duty specific stations, but trucks can also fuel at either or. We do have about 100 plus in development that should be coming online soon. But also the state of California signed an executive order mandating 120 or more stations by 2025. And this is just in light duty. Let's shift to some economics here. So I won't go into too much detail today, but just to give everybody some information that the California Fuel Cell Partnership just released back in July, a document outlining kind of a vision for the future of a hydrogen society. I suggest you all take a look. It could be found on the website that I've listed on the screen. But it does talk about economies of scale and technology going forward. So the next challenge was kind of fleet flexibility. So back at Convec 2021, SAE International's conference, my colleague Luke Rippelmeyer presented on a years-long study with Toyota and NREL. They had collaborated to identify and extrapolate statistically relevant duty cycles that have now been made public on NREL's website. Ultimately, the team has concluded that different usage cycles require different technologies. Something that fuel cell might be perfect for, maybe battery isn't, and the other way around, and other technologies that could be available in the future. I suggest you take a look at the study. If you have other questions, feel free to reach out. But this is a good start at looking at the commercial truck drayage cycle, regional cycle, transit buses, long haul, and local delivery applications that zero emissions could be getting into in the future. So where are the other opportunities? Toyota has announced various applications for the fuel cells that are currently being developed, whether it's a medium duty truck, heavy duty truck here in North America, stationary projects, passenger cars like the Mirai. The opportunities are boundless. So just because we're doing Project Portal doesn't mean that we can't do anything else. We're a mobility company now, so looking at all the different modes of transportation. So in summary, we want to share that Toyota is moving forward with a fuel cell electric powertrain kit that manufacturers of trucks, Class A trucks, and other commercialized fleets can convert their diesel fleets into a zero emission truck. With that, I'll turn it back over to Chris, and we can go through some questions if there are any in the chat.
Yes, thanks for the presentation that Scott mentioned. The chat function is open for any questions that you may have. So I'm just going to kind of start at the top, and I'll try and consolidate as we go through. But maybe Scott, I'm going to ask these questions to you, but I'll pop in and give some additional comments. So first question is from Jeff. At what pressure is the hydrogen stored?
Yeah, so hydrogen stored in the tanks on Project Portal is at 70 MPa. This is the storage pressure for the California stations and the light duty Mirai as well.
Yeah, so I'll just mention, for those not so familiar with the hydrogen storage, there's a couple different storage protocols or pressures that, depending on the application. So for instance, 35 MPa is typical for transit bus or some other application. So the truck and the tanks and the fuel system are designed to work, as Scott mentioned, to 70 MPa. But of course, can function lower than that, because obviously the pressure comes down as you use the fuel. So it's possible to fuel at a station that's only capable of 35 MPa as well, to fuel these trucks. Okay, so Ramesh asks a question about the purpose of the HV battery and how the capacity was determined, and whether the battery is in series or parallel with the fuel cell stacks.
Right, so a few questions in that one. So the battery is used similar to how we have on our hybrid powertrains today. So instead of an internal combustion engine, we have our fuel cell stacks. So we're using them in conjunction, in parallel with each of the battery to provide power during high load conditions, or energy will go back to the batteries during regenerative braking. So being able to size the battery accordingly based on the power demand of the cycle, we're able to determine that the cycles that our truck OEM partners have been requesting us to meet or exceed in terms of the power demand has dictated kind of the additional power that we'll need on top of the fuel cell. So they're working in conjunction with each other. It's not a series setup like some other fuel cells out there, where a fuel cell is just used as a generator to charge up the battery, and the battery is the main power. That's not the case with our electrical architecture.
Okay, thanks, Scott. Next question from Jacques. What percent of components are sourced in North America?
So I can't actually answer that right now. I'd have to look back on that. So maybe Chris will have to take.
Yeah, maybe I'll add a couple general comments to that. So the system, the kit that we're providing is a mix of North America and outside North America components. I mean, as we mentioned, the fuel cell stack, the modules are being produced by our parent company, TMC, Toyota Motor Corporation in Japan. Those modules they announced as being available for a lot of different applications. So we're sourcing those modules from Japan, and then combining those. So for instance, that fuel cell module is a combined module that was shown in the video, and a couple of the pictures basically is taking two individual modules, combining them together with all of the cooling circuitry, bracketry, everything that's required, and you know, most of those components are, you know, are ones that would be sourced here in North America, and between battery and hydrogen cabinet, you know, it's a mix. So but we haven't completed all of the, you know, the detailed sourcing on these components yet, so that will change, or, you know, fill in the blanks basically over time. Sanjana asks, is it a switch between battery and fuel cell depending on the route, or do they both operate together? I think you commented on that a little bit, Scott, but maybe if you can touch on that again.
Yeah, so it's a combination of both. There are times where only the fuel cell will be driving the main propulsion. The battery will support in high load conditions. We will have capability to do battery only if need be. But for the most part, in the power split logic that we have, it's kind of a shared load between the two. Okay, and then a question about from Felix, the power output, the 160 kilowatts, is that net or gross, or how is that specified? And also, how do you manage the stack degradation? Yeah, so the 160 kilowatts is the two fuel cells put together. That is net, so taking into consideration any of the balance of plant loads coming off of it. So hydrogen pump, the water pump, and the air compressor. I'm sorry, the second part of the question, Chris?
So yeah, is basically about service life and how to manage the stack degradation over time.
Right. So the battery allows for keeping the IV curve of the battery of the fuel cell in a stable condition. So even though we're fluctuating the power output of the fuel cell at times during the drive cycle, we're still able to keep the voltage and the IV curve, the current voltage curve, in a range that can handle or at least expand the lifespan of the fuel cells themselves. But it is something that we do actively look at.
And Corey is asking about the hydrogen that we're using in the system and how that's produced. So are there different methods for producing hydrogen and storing it? And then again, at the pressure, I think we commented as well, the system operates at the 70 MPa protocol. But maybe if you can give a couple comments on hydrogen production and storage.
Yeah, so hydrogen production. So our hydrogen we get from our stations and the station providers. So there's a various number of hydrogen suppliers out there that are providing to these third-party stations in the state of California. I can't necessarily comment on whether if it's green hydrogen, blue hydrogen, or gray hydrogen, or if it's made by electrolysis or other means. But there's a variety out there, and I'd have to do a little bit more digging to determine exactly where all the hydrogen is coming from in the state of California.
Yeah, so I think just to make some comments on that in general. So I mean, as far as the truck is concerned, you know, hydrogen is hydrogen, right? We're running on the fuel that's available, and I think you know, in general, you're seeing a shift from a lot of the hydrogen that's produced now, you know, moving from a gray to a blue to a green type of technology to be, you know, better, obviously, for the environment. So I think there's a move there. Of course, you know, that's a bigger kind of discussion from an infrastructure side. Where's the hydrogen produced, the logistics for moving it, things like that. But I think in general, as far as kind of hydrogen society discussions, there's a lot involved there. But you know, the key point is having the vehicles at the end that use the hydrogen drives the production. And you know, if there's not a lot of vehicles using hydrogen, then, you know, obviously probably the current or the old production methods for hydrogen is what would be used. By getting vehicles out on the road and really pushing the adoption of the technology and pushing for growth of hydrogen consumption, you know, it makes sense that a lot of the newer production methods are being used on new facilities that go online. So that shift.
That's exactly right, Chris. And like looking at economies of scale, right? The amount of hydrogen consumed in the heavy duty trucking space versus the amount of hydrogen that would be consumed by a light duty vehicle, such as the Mirai, is almost tenfold. So looking at kind of the demand on the hydrogen infrastructure and network in the future as companies transition to either a hydrogen fuel cell Class 8 heavy duty truck or other hydrogen based applications, that is only going to push further into new ways of securing hydrogen, producing clean hydrogen, and so on.
Thanks, Scott. Next question from Andrew is, Toyota's known for high quality and standard processes. How did you leverage Toyota's strengths on this project to meet the challenges to innovate so successfully and launch this new product concept?
Yeah, that's a great question. So as we had gone earlier through the presentation, our alpha proof of concept was very much a proof of concept. We took two Mirais, tore them apart, put them together and added a couple extra components and saw if it worked or not. From there, it was just this in the spirit of Kaizen, or kind of continuous improvement, that each step along the way, each iteration that we had gone through, whether it's our beta prototype or working with our Kenworth partners and in the Zanzef vehicles, and then kind of moving towards the next generation, we've learned something, actually learned quite a bit each step of the way to kind of get to that level of quality that our customers know and love about us. We've also been able to go from a small research and development team to now leveraging the power of Toyota, looking at our manufacturing facilities and quality teams. They all have eyes on it now. So as we're gearing up with Toyota Motor Manufacturing Kentucky, those quality checks that we have in place for our light duty vehicles are going to be more and more prevalent in the fuel cell powertrain kit that we're developing now.
Okay, next question from Rod. Without compression release brake, or Jake brake, which I think you mentioned earlier in the presentation, is regenerative braking sufficient for Class 8 payloads? Or is there some other strategy that's used to extend the service brakes?
Right, so that's definitely something we're currently studying. Looking at the amount of capacity we have in our battery to capture that regen, to provide enough regenerative force going down a steep grade at 80,000 pounds. We are actually doing that testing now to make sure that our targets were set appropriately. There are other solutions out there, either brake resistors or retarders and so on, but those are things that a truck OEM would be more apt to go with in their packaging. But it's definitely something that we're taking a look at and that we're applying to the duty cycles that we're asked to achieve.
Yeah, maybe, and I'll just add a little bit onto that as well. When we originally kicked off the project, this was intended for port drayage applications. So there's a couple bridges in the area, but not a lot as far as hills and things like that. But turn the clock forward several years, and as the environment in California has changed and the move towards more regulation associated with implementing zero emission technology on heavy duty trucks, we had to look at regional route and other applications in the state. So the simulations, as we would look at routes and the battery size did change over time, but it's a balance, right? Because of course we can recapture all of the energy by putting a really big battery on the truck. But again, the issue with a big battery is the reduction in the overall payload. In California, Class 8 truck is 82,000 pounds as far as a GVWR. So every additional pound of battery that you have on the truck is one less pound of cargo that can be moved. So there is a balance there. I think one of the key things is, even just in the last couple of weeks, we finished several days worth of testing on one of the trucks on the Grapevine route in California. That was able to give us some validity as far as our modeling goes. Anyway, yeah, I mean, it is an issue, right? Because we want to recapture as much energy as possible. If we use a brake resistor or some other technology, then we're turning that energy into heat, right? And we're rejecting it, and we don't want to do that. So we want to try and recover as much as possible without relying too much on the service brakes. So thank you for that question. From Nelson, how does the price of hydrogen compare to diesel?
Yeah, so kind of going with the economies of scale, as we don't have so much hydrogen in the market right now, and the way that it's being captured, Obviously, there's a price discrepancy between diesel and hydrogen. Kind of the long-term plan would be that as more and more trucks get into the market and require hydrogen at larger scales, the overall cost will go down. As I had pointed out earlier later in the presentation, the California Fuel Cell Partnership actually did a pretty phenomenal study on kind of that cost reduction over time. So I highly suggest maybe going and taking a look at that.
Okay, next question. Sorry about the pronunciation. Blaumanu asked a question about, I want to make sure I get the essence of what we're asking. He says hill stations and oxygen is less. So my assumption he means high altitude. So any comments on testing that's been done at high altitudes or places we've taken these trucks?
Yeah, so I see you smirking, Chris. So one of the areas that we've actually tested the truck, Kenworth actually took one of the Zanzev trucks up Pikes Peak. And from our understanding, and maybe some of the Kenworth guys on the call will attest to that, it performed admirably. Our fuel cells are tested up to 3,400 meters, I believe. So looking at that, and looking at Pikes Peak and the performance that we had, I don't think we've run into a problem yet.
Okay, yeah, thanks for that answer there, Scott. And then from Lars, is Toyota working on electrolysis for H2 production in addition to fuel cell mode? Or so basically, are we working on the hydrogen production side, or are we more on the hardware side?
So I can't really comment on the hydrogen production side. We work with a lot of our partners, different companies, both in California, in Europe, and also in Japan, to develop new technologies and make it so that that technology can proliferate. I don't know off the top of my head if there's any specific projects going on.
Yeah, I guess I'd just add to that. We talked about the source of the hydrogen. So the truck's happy to use whatever hydrogen we get. Obviously, I think electrolysis is an emerging technology there as far as generating the hydrogen. So
yeah,
oh, go ahead.
I will say one thing that we did announce during the Zanzev project, that Toyota worked in conjunction with another company, I believe Shell, on a trigen station, basically taking biomass and converting it to hydrogen, electricity, heat, and water. So that's a technology that was co-developed, but I think you guys can learn more on the internet about that project.
Okay, Nisar asks the voltage level of the kit. What voltage are we?
So the voltage level can differentiate between 400 volts and 750 volts. 750 being on the high side at high SOC. But that's basically the level that we're comfortable with in the kit.
Okay. And from Eric, could the same performance, payload, and fuel range requirements be met if this were a full battery electric versus fuel cell electric? And do you see fuel cell electric spreading to the mainstream, maybe even on the light duty side?
So it's a great question. Looking at duty cycles and looking at the study that our colleague Luke did, there are applications that are best suited for battery electric vehicles, and there's applications that are best suited for fuel cell. Looking at fill times as an example, if you're doing something more in the long haul range, it would make more sense to have a fuel cell electric that can fill up in 15 to 20 minutes versus a battery that will have to sit overnight. Looking at kind of the usable energy on board for a high voltage battery versus what could be stored in hydrogen tanks for a fuel cell, there is kind of a range discrepancy off of kind of one full state of charge. So I would say that there's room for both. Both technologies are applicable, maybe not for the same duty cycle though.
Okay, we talked a little bit about the cost of fuel. How about thinking more bigger scale, looking at the entire total cost of ownership. So what's the cost comparison between fuel cell and diesel when you include the manufacturing and servicing? So, the parts cost and everything from a TCO perspective.
Yeah, I think it's a great question. It's a question that everybody asks. We can't really comment on the cost of the kit itself. As Chris had mentioned earlier, we're still finalizing those types of activities. We do have our targets, but I think for right now, we'll have to wait and see once we announce something in terms of cost.
Okay, yeah, so I think in general there, maybe just a couple of comments on that. I think, obviously newer technology does cost more money, and there are, in the near term, at least in the states like in California, there are, pretty significant incentives that are available on zero emission vehicles, more so on fuel cell than battery even. So I think what we've seen previously on new technology, even on the battery electric side, is those incentives kind of help to bridge the gap as the volume's increasing, to bring down the cost of the hardware, right? When you're low volume production, the hardware is more expensive. When you scale it up, the hardware costs come down. So those incentives really play a role in helping to bring those costs down. So I think the image is, we don't so much look at the cost of fuel and say, hydrogen will be X versus diesel in the future, therefore it's less expensive. It is Stuart, as he mentioned, kind of what's the overall cost story, total cost of ownership. So it's all of those things. It's the parts, it's the fuel, it's the service. And basically the image and the research and our modeling shows, as part production goes up, as fuel costs come down, the total cost of ownership, we think, is very competitive to diesel, or even less than diesel in the future. And therefore, it really helps to take that issue out of the story, right? If the cost story goes away, why wouldn't you use a fuel cell vehicle versus a diesel vehicle?
Absolutely.
Okay, and let's see. Govind asked which of the different applications may need more than 2 fuel cells, mining or agriculture or things like that. Are there other applications maybe that would require more than the 2 modules that we're using in this Class 8?
Yeah, I think that that's something that we've looked at, obviously with the study that we did with NREL, looking at those power demands for mining vehicles and kind of heavy duty, more so than Class 8. The target that we set out in the market that we're looking to provide fuel cell, a fuel cell kit to, would start off at the Class 8 level. Once we're comfortable with that, maybe we take a look at the other duty cycles, but for right now, that's kind of been on a lower priority.
Okay, and then George is asking about the battery capacity and using predictive methods, navigation, things like that, e-horizon type information for helping precondition the SOC of the battery. Any comments on that?
Yeah, so like we had mentioned in the presentation, the battery is at 200 kilowatt hours now, but it could be different based on what our customers are asking for and what the duty cycles are needed to complete. We definitely want to look at that aspect in the future, as well as fuel cells become more powerful for generations to come, looking at the battery sizing as well. I maybe missed your second part of the question, Chris.
It was more about, just preconditioning the battery.
Preconditioning. So I know that there's a lot of patents out there from other companies about kind of the precondition. We do have some technology and controls logic for, let's say, burning off extra energy in a downhill. But for right now, that's been kind of another lower priority at the moment.
Okay, next question. We might not get through all of these, so that's
Okay.
good. From Bamnu again, regarding any technology that's used as like a turbo booster, maybe sending more oxygen to the fuel cells, or in our system, do we is the battery kind of our turbo booster?
Right. Yeah. Short answer is there's nothing in the fuel cells that will hit it with some knocks or something. But we do use the battery as kind of that boost of power at the higher C rates and stuff like that. That we provide the maximum amount of power to the motor as needed or as demanded by the truck side.
And then Jose is asking, outside of California advancing the technology, are there other states and maybe their ports or other areas that are interested in this technology?
Yeah, there's definitely been discussions going around, whether it's on the West Coast, those ports out in Portland or Washington, also East Coast, Boston area, New Jersey, New York. So far, there hasn't been any movement towards kind of incentives or programs, but it doesn't mean that it's not going to happen. We're actively looking towards the future for those.
Question about from Govind about any areas that are continuing to pose challenges. So, for instance, cold start or hot weather. Are there places that we talked about high altitude? Are there other places that we test these trucks for extreme temperatures?
Yeah, I mean, great question. We've, as some on this call may know, our Arizona Proving Grounds in Whitman, Arizona gets pretty hot during the summer. We've had trucks running out there over the summer, over 100 degrees for multiple days. We've been able to test them pretty rigorously. We also do have cold start capability on our fuel cells, the Mirai itself on the light duty side, but we are still actively testing. So it is in the testing phase, evaluation phase now for those specific conditions. High altitude, likewise, we going up to Pikes Peak and other high altitude areas in the state of California.
Eric asked a question about perceptions of hydrogen. Are people afraid of hydrogen because of things like maybe in the past Hindenburg, or they just don't know about it? Or any comments on that?
Yeah, I think that there may be some preconceived notions of hydrogen. Definitely in the past, people have thought that we'd be burning hydrogen as a fuel source. So to get it out there, we're converting hydrogen into electricity and water. And I think it's a good opportunity, especially forums like SAE Detroit and other areas, to kind of educate, kind of show the new technology, show that it produces an enormous amount of energy and that it's safe. We have, like I had mentioned, in 2014, we released the Mirai, and it's been on the road in customers' hands safely for a number of years. So I think that tide is turning, but there's still maybe a little bit of ways to go.
Okay, I think maybe we only have time for one more question. So Suvith asked a question about range, and how far do these trucks go, and or I guess, are there methods to get more range as well?
Yeah, so like we had mentioned in the presentation, going around 300, 350 miles per fill up. It's highly dependent on things like payload. So if you're at 82,000 pounds GCW versus 60,000, there's quite a significant difference in fuel economy. If you're looking at the duty cycles going up a steep grade for the majority of the duty cycle, obviously the fuel economy takes a hit. So like I had mentioned also, the study that Toyota did with NREL looked at a lot of those duty cycles and looked at what a typical drayage profile would look like, or regional haul, and kind of playing those scenarios out both in simulation and in the real world, like what Danny was driving around was our latest prototype. those are constantly gathering data and trying to kind of have a concise look at fuel economy.
Okay, thanks, Scott, and thank you to everyone for all of the great questions. I do apologize that we weren't able to get to everyone's questions, but we'll go through them and see if there's some good topics in there, and we can address those maybe each by each. In closing, I'd like to thank you to everyone for taking the time to join us here today. I appreciate you investing an hour in what we wanted to talk about. If you do have any questions or additional inquiries, please go ahead and just reach out to the section at events@sae-detroit.org, which is shown there on the screen. And we will, they'll pass those along to us, and we'll get back to you. So thanks again for joining, and have a great rest of your day.
Thank you, everyone. Take care. Have a good one.